about what we're getting into today because we are literally unlocking an entirely invisible universe. We're talking about the microscopic world, a space that dictates the properties of everything around us, yet stays completely hidden from our naked eye. So get ready, because today we are mastering the nanoscale. Right off the bat, here's the fundamental challenge. How do we actually visualize structures that are 100,000 times smaller than a single human hair? Standard light microscopes? Yeah, they simply can't handle this. The physics of light just won't allow it. To truly see nanomaterials, we need the ultimate solution in characterization technology, field emission scanning electron microscopy, or as we'll call it, FESEM. I know, it sounds like a mouthful, but as you'll see by the end of this explainer, it is an absolute game changer. Okay, let's dive into our roadmap for today. First, welcome to the nanoscale. Second, how FESEM actually works. Third, prepping your nanosample. Fourth, imaging best practices. And finally, complementary tools. All right, kicking things off with Section 1, welcome to the nanoscale, unlocking unseen worlds. I mean, just look at this number, greater than 300,000 times magnification. FESM doesn't just magnify things a little bit, it takes us on this breathtaking journey deep down into the actual architecture of matter. To put that into perspective, if you magnified a standard glass marble by 300,000 times, it would be roughly the size of the Earth. This massive capability lets us get incredibly close, turning the totally invisible into something we can analyze right on our screens. And, with that massive magnification comes stunning clarity. We're talking about ultra-high resolution down to roughly 1 to 1.5 nanometers. That means we can clearly distinguish tiny features that are practically right on top of each other. But beyond just raw resolution, FESEM gives us a wonderfully large depth of field, so your images actually look three-dimensional and crisp across different focal planes. Plus, the tech produces minimal electrostatic distortion, meaning the image you're looking at is an incredibly faithful representation of the real thing. And honestly, this image perfectly illustrates what that power yields. Look at these typical FESEM images of nanomaterials. We aren't just staring at generic blobs here. You can clearly identify distinct, beautifully defined shapes. Over on the left, check out those perfectly round nanospheres. Right next to them, you can trace the long, hollow channels of nanotubes. Then we've got this sprawling, web-like network of nanowires, and finally, the delicate, folded layers of nanosheets. Each one of these behaves totally differently in real-world applications, and being able to literally see them, it changes everything. So the crucial takeaway here is this. FESM is giving us highly detailed topographical information. These aren't just pretty pictures for a textbook. This incredible imagery gives us critical, quantifiable data. We can measure exact sizes and shapes. We can see exactly how particles clump together, agglomeration and dispersion. And we can analyze their surface topography. Are they smooth, rough, porous, defective? All this data is absolutely essential for the scientists engineering our next generation of materials. Moving right along to Section 2, how FESEM actually works, tracing the beam. So how does this magic actually happen? Well, instead of light, FESEM uses a beam of electrons. It all kicks off at the very top of the machine with the Field Emission Gun, or FEG. A massive electric field is applied to a really sharp tip, which physically pulls electrons out. This creates a beam that shoots straight down the column, passing through a series of lenses. Eventually, this highly focused electron beam hits your sample mounted on the stage at the bottom. That interaction between the beam and the sample creates signals, which are then scooped up by detectors to form the image we see. Inside that main column, it is a marvel of precision engineering. The beam gets accelerated by the anode and then perfectly focused by electromagnetic lenses, like the condenser and objective lenses, refined by the aperture and scanned across the sample by the scan coils. But listen, none of this works without the vacuum system. Maintaining a high vacuum, an environment literally emptier than low Earth orbit, is absolutely crucial. If there were air molecules floating around in that column, the electrons would crash into them, scatter everywhere, and completely ruin the beam. The vacuum ensures those electrons travel smoothly from the gun all the way to your sample. Now, what's really fascinating is how we collect the data once the beam actually hits the sample. We primarily use two different detectors. First, the secondary electron, or SE detector. This guy collects low-energy electrons knocked right off the very surface of your sample. This is what gives us those gorgeous 3D topographical images showing texture and shape. On the flip side, we have the backscattered electron, or BSE detector. This collects higher energy electrons that bounce back from deeper within the sample. And the cool thing about BSE is it gives us compositional contrast. Heavier elements bounce back more electrons and show up noticeably brighter, giving us massive clues about what the material is actually made of. Let's jump into Section 3, prepping your nanosample, the workflow. Getting uniform dispersion is the absolute goal here. You can't just throw dust in the machine. First, we disperse the nanomaterial in a solvent, typically something like ethanol or acetone. Second, to break up any stubborn clumps, we pop it in an ultrasonic bath and sonicate it. Those sound waves literally shake the particles apart for a nice, uniform dispersion. Third, we carefully drop cast this liquid suspension onto a conductive substrate, usually a silicon wafer or some special carbon tape. Finally, we just let the solvent completely evaporate. What's left is a dry, beautifully distributed sample, perfectly ready for the vacuum chamber. But wait, what if your material doesn't conduct electricity? Remember, we are literally shooting a high-energy beam of electrons at it. If the sample is non-conductive, those electrons will just build up. It creates intense static electricity, a super annoying phenomenon we call charging, which totally ruins the image. To fix this, we use a sputter coater. Think of it like giving your sample a conductive metal winter coat. We apply an ultra-thin layer, we're talking just 5 to 10 nanometers thick, of gold/palladium or platinum. It's thick enough to carry that static charge away, but thin enough that it doesn't vary all those tiny nanoscale surface features we're trying to look at. Moving on to Section 4, imaging best practices, getting the perfect shot. Look, when you're sitting at the controls, these parameters matter immensely. If you're working with beam-sensitive materials, you have got to use a low accelerating voltage, ideally between 1 and 5 kilovolts. You also need to avoid high beam currents and lingering way too long on one spot. Why? Well, because that electron beam packs a punch. If you blast a delicate polymer or a biological sample with a high-energy beam, you will literally melt or destroy the exact thing you are trying to photograph. And finally, you have to continually optimize your working distance. That's the physical gap between the objective lens and the sample to find that perfect sweet spot between resolution and depth of field. Let's wrap up with Section 5, complementary tools, the broader ecosystem. Time for a quick reality check. FESEM provides magnificent details, for sure, but it only provides surface morphology. At its core, it's a topography tool. It cannot reveal the internal crystal structure of your material. It can't see inside the nanosphere. And furthermore, despite its crazy high resolution, it gives us zero atomic level information. So, what do? Well, we don't just give up. We rely on a broader ecosystem of laboratory tools to fill in those exact gaps. When FESEM hits its limit, we call in the reinforcements. Need to know exactly what elements make up your sample? We use EDS, or Energy Dispersive X-ray Spectroscopy. It attaches right onto the FESEM and gives us quantitative elemental mapping. Need to look inside the structure? We turn to TEM, or Transmission Electron Microscopy. TEM shoots electrons straight through an ultra-thin sample to visualize internal structures and core shell boundaries all the way down to 2 nanometers. And hey, if you need to know how big your particles are while they're actually floating in a liquid, their hydrodynamic size, you use DLS, or Dynamic Light Scattering. And this right here perfectly captures the whole philosophy of material science. No single machine does it all. FESM is an unbeatably powerful tool for nanoscale surface characterization. But if you want to truly understand a nanomaterial, to know its structural and compositional identity completely, you've got to combine FESM with these complementary techniques. It is a massive team effort at the microscopic level, which leaves us with this final thought. Now that we have the power to clearly visualize, measure, and map structures 100,000 times smaller than a human hair, what comes next? FESEM has unlocked the very surface of the nano world for us. So, from creating stronger, lighter building materials to developing highly targeted drug delivery systems, how will mastering these exact nanoscale insights drive our next big technological breakthrough? It is a deeply fascinating question, and one that scientists in labs all over the world are answering as we speak. Thank you so much for exploring this incredible microscopic universe with me today.